Alright, children, it's late on Monday night, getting close to midnight, and while I'm recording this, so I'm going to do the best job I can at not yawning, which is not going to be easy for me. So, there's a system of writing coordinates that's different than the one you practiced with so far in your life. The one you're used to dealing with is called the rectangular. The rectangular coordinate system, X and Y. Well, this one's called polar coordinates. And instead of dealing with, why is there something on my screen? Instead of dealing with rectangles, you're going to be dealing with circles. So the center, instead of being called the origin, is called the pole. And every point on that graph has a coordinate with an angle and a radius. Now this particular picture that you see here on the right is polar graph paper in degrees. Now, there's obviously a lot more degrees than the ones we see there, which reminds us a lot of the unit circle. But in this particular picture, a polar coordinate. Now, if you go back to rectangular coordinates, how do I list this rectangular coordinate? Well, this side would be called X and this side would be called Y, and so we could call this coordinate X, Y. Now, what are we really doing? We are really and truthfully following the legs of a right triangle. But that's not what happens in polar form. In polar form, instead of following the legs, we rotate a certain number of degrees, and then we move to the landing or stopping point. So, rotate and then move to the correct radius. Now, we can talk about this rectangular coordinate and this polar coordinate, but truthfully, we're landing at the same place. Hopefully, I hope you realize that that's setting us up for being able to change things back and forth between rectangular form and polar form. Plotting points in the polar coordinate system. Now, the one thing that I do not like about this book is the way they write their polar coordinates. When I was growing up, back in the day, we would use brackets for polar coordinates. I'm not sure why they don't. So we rotate to pi over 3, that's 60 degrees. And we move out 2 units. 1, 2. Sorry for the yawn again. So this is the point they're calling P. Pi over 3 was the rotation. 2 units is the length of that particular, or the coordinate. Let me choose a different color for Q. 3 pi over 4. Now, you're probably wondering, you're probably saying to yourself, 3 pi over 4 isn't down in quadrant 4. Well, where is 3 pi over 4? Well, that's actually halfway in the middle of quadrant 2. But then I noticed right here we have a negative radius. A negative radius. That's going, instead of moving forward 1 unit, we moved backwards 1 unit. So we can rotate and walk forward away from the pole, or we could rotate and then walk backwards. Walk backwards away from the pole. So we could do either one. There's forwards and backwards. I need to try to wake up. This is ridiculous. So point Q is this point down here. It is 1 unit away from the pole, or the origin. So we rotated around to 3 pi over 4 and then walked backwards. That's kind of weird, you know. Most of us don't think like that. Well, then we have this one over here for letter C. Man, it just drives me nuts that they're not using brackets. Now, that's how we normally write our coordinates. At least that's the way I've always written it. R theta. Okay, so negative 45 means I'm rotating. Whoa, that was not negative 45. Holy cow. Who did that? So negative 45 is a rotation down here, right? And then walking positive 3 would, so this would be the point that's 3 units away from, so R is down here in quadrant 4. So that's how we rotate. We rotate, then we either walk forward like we did in example A and C, or we walk backwards like we did in example B, or 1B I should say. This first video is going to go through example 1, 2, 3, and 4, and then I want you to switch over to your homework for today, and then we will work on the notes for the rest of the section and the problems tomorrow. Okay, so if the point P has coordinates 3, 3 pi over 3, find all the if the point P has polar coordinates 3, I see what they're saying. They're saying that there are other polar coordinates that have that same location. Okay, so let's think about this. So pi over 3, and you walk out 3 units to get to that. So that is one way to get to that point P. What else could we do? Well, we could rotate all the way down to this direction, but instead of walking forwards, we could walk backwards to get to that same place. Alright, so what would that look like? Well, obviously, since we would be walking backwards, it would be a negative 3. But what would the angle measurement be? Because you're going halfway around the circle from pi over 3. So I guess that's going to be whatever pi plus pi over 3 is. Well, that would be 4 pi over 3. Okay. What if we rotated in a negative direction and then walked backwards? All right, we could do that so that we definitely have a negative 3 there. But what is that negative rotation? Wait a second, I think I drew my circle there on my, just a little bit too far. There we go. Well, if 4 pi over 3 was going around, then it would be negative 2 pi over 3. Okay. What about if we did this? Came all the way around there, and then we walked forward 3 units. So this is going to have a positive 3. And I believe that would be a negative 5 pi over 3. Yeah, that's right. So those are the positive rotations and the negative rotations and the radius for each one, and all of those should land on letter P. Now, you can get more generic with finding all the polar coordinates. Notice that the positive rotations were adding even multiples of pi. If I come up here and just take a look at, these two right here, the ones with a positive rotation or positive radius. Notice that the distance between the thetas is 2n, or is actually 2 pi between those. Now, if you'll notice, the connection between this one and this one is right here. It is only 1 pi unit different. So to jump from the original, if you are keeping the radius positive, you either add or subtract an even multiple of pi. But if you want to change to a negative radius, then you only want to add an odd multiple of pi. So that's what you're getting in this theorem right here. Okay, so you can see here that you've got this r, your original r theta, and if you keep r positive, then you can add any multiple, any even multiple of pi, like 2 pi or 4 pi or 6 pi, or you could go negative 2 pi, negative 4 pi, negative 6 pi. But as soon as you want to switch this to a negative, you'll notice that this, which looks weird, is an odd multiple of pi. 2n plus 1. You stick any number in there you want. Stick a 5 in there, stick a 3 in there, stick a 1 in there, stick a 2 in there. What you will end up with is an odd number times pi. Like 1 pi or 3 pi or 5 pi. Now, we want to talk about coordinate conversion equations. How do I switch back and forth between the polar form of equations and the rectangular form of equations? Because if you take a look at this particular scenario, x is equal to r cosine theta. That's just, adjacent over hypotenuse kind of stuff. And y is equal to r sine theta. Also basic, just SOHCAHTOA stuff. And then if we get into x squared plus y squared equals r squared, that's just your Pythagorean theorem. And of course, tangent of theta is y over x. So how do I handle example 3 here? Find the rectangular coordinates of the points which give. Okay, so let's see here. All right. So use approximate exact solution values with a calculator when appropriate. Okay. So x is equal to r cosine 5 pi over 6. Y equal to r sine 5 over 6. Need to get a different color. So this x value would be 3. The cosine of 5 pi over 6 is negative radical 3 over 2. That would be 3 sine 5 pi over 6 is 1/2. So 3/2 is my y value. And negative 3 radical 3 over 2 for the x value. Now on the second one here, I would definitely have to use a calculator on, right? Because to cosine negative 200, that's not going to be nice. Y equals 2 sine negative 200. You'd have to use a calculator on both of those because there's no way anybody's going to know them off the top of their head. So we'll go on to example 4, which will be our last. Alright, so example 4 here. we have the coordinate at negative 1, 1. That's our rectangular coordinate, negative 1, 1. We want to convert that to polar. Now, remember what you have here. You have a right triangle. So we can do the inverse tangent of opposite over adjacent. Right? We could say theta's down here. Inverse tangent of opposite over adjacent. And when we do that, we get negative pi over 4. And remember, you're simplifying the inverse tangent feature, which means you are looking for only one answer. Now, how am I going to use that? Wow, my theta looks like an evil dude with a big mouth and 2 little tiny eyes. So, negative pi over 4 is down here. But we want to walk backwards. So, we come down to negative pi over 4. And then we walk backwards till we get there. I think that's good enough. So I need the radius, right? So that'd be 1 squared plus negative 1 squared equals c squared. So that's 2 equals c squared. So c equals the square root of 2. That's how we figure out that. Okay. We found the distance, we found the angle. So we could actually write this coordinate as negative square root 2 and negative pi over 4. Or we could say positive radical 2 and 3 pi over 4. Just the 3 pi over 4 would make me rotate to here, and then stepping radical 2 units away from the origin. Okay, now on this example right here, negative 3, 0 is right on the axis. I don't even know if I can, what am I going to do? I think the whole inverse tangent thing is not going to work, right? Let's see here. I'm trying to think if there's anything more difficult than what we have going on right here. Because it's on the axes. 3 units to the left, find 2 polar coordinate pairs. Well, we're just going to find 1 polar coordinate pair. Oh, well, okay, that's dumb. So 3 pi would work. 3 negative pi would work. Negative 3, 0. Polar. And negative 3. 2 pi. Okay, that's enough for this video since it's 12:30 in the morning. Sorry for the late notes, and I'll have this video up and running shortly.